Hi, this is Ernie. This video is going to show you a little bit of fun with a ping pong ball cannon and some of the science you can do in your own workshop at home, and I hope you enjoy it. First off, let's show you what a ping pong ball cannon is. What you see here, it's pretty simple. This is a 1.5 inch ID PVC pipe, Schedule 40, with 2 end caps on it, and we've sealed the end caps with party balloon material, the metallized plastic party balloons, and we sealed both ends. Just inside the end here is a ping pong ball resting there, and here's a vacuum line. We pull a vacuum on that tube as much as we can, rupture this end with something sharp like scissors, and the ping pong ball flies out the other end at 600 miles an hour. Lots of fun. I'm going to show you how to load up my ping pong ball cannon. First off, you need a ping pong ball, of course. And this ping pong ball is nice fit, but it's loose enough it will roll. So to keep it from doing that, just put a little piece of paper and put it up next to it. And that barely holds it, keeps it from rolling. You could screw this in far enough that it holds it, but this paper works better. Okay, that's a new process I use. Then you take what some people call mylar balloons. These party balloons, they're not mylar, but they're metallized plastic of some sort. You cut that up into squares. Now when you cut it up into squares, they get to be these fussy little curly things. So you gotta unroll that, and if you're an old guy like me, that can be a little tricky. Now this is the end cap off the PVC. I have drilled it out so that the ball clears all the way through. You might just be able to use a splice fitting and do the same thing. Main thing is you gotta let the ball go all the way through. Unroll this, get it on here, make sure you get it centered, no wrinkles, and then slide this on like so. And there you go, airtight seal. The way you can tell for sure is when you go to air it up, if you're not getting as much vacuum as you think, you may be getting a leak on here. You can put your hand on here, and if you feel suction, you know you got a leak there. Now you do the same thing without the ping pong ball. You put a foil and end cap on the other end, just like this. And when you go to launch it, you pull as much vacuum as you can, then you pop that with something sharp. The ball shoots through the other end at 600 miles an hour. At the other end down there, we have a pop can sitting there, and there's another camera videotaping that to see what's going to go on. But we're going to shoot this thing through a pop can and let you see what it does. Now, what I have here is a 2-stage vacuum pump from Harbor Freight. The more vacuum you can pull, the better. I have a pressure gauge here, digital pressure gauge, hooked up through this manifold so I can monitor the vacuum at the same time I'm pulling a vacuum. Now, a few days ago, I was getting 14.21 psi of vacuum in this tube, but in the last few days, that has dropped. I don't know if the pump's getting old or if I have a leak somewhere. I'm getting more like 13.9 psi, but that still works pretty good. So what I do is turn this on, watch this until it gets to where it's about as good as it can go, and then I puncture the tube. Let's have at it. Okay, it's up to 9 psi, 10 psi, 11, 12, 13, 13.7, 0.8, 13.9, 14.1, 13.97. That looks like about as far as it's going to go, 13.97. So here we go. Ready? There we go. Turn off the pump. Now let's go see what I did to that pop can. Okay, there's a pop can. Zoom up on it. And it blew a hole right through it. And you can see where I've been doing a number of these where I have ping pong balls stuck in the wall of my, in the garage door for my shop. So we've been shooting a lot of these off. 13.97. That looks like about as far as it's going to go, 13.97. So here we go. Ready? Well, that tells you what a ping pong ball cannon is and how it works, and it can be lots of fun. A lot of people on the internet have done this. I've seen a lot of YouTube videos, and one of those was Mythbusters. They did a pretty extensive look into them. When I made this thing, I was guessing that I would get 300 to 500 miles an hour out of the ball. As I noted earlier, I said that this thing does 600, and that's the result of the experiments we did here. I promised you some science, so let's get into that. First thing we need to do is measure how fast it really is going. And to do that, well, the first method I'm going to use is I've got some high-speed cameras. I don't have the really expensive one like the slow-mo guys, but I do have a couple of old Casio Exilum cameras, and the one I will be using here is the EX-F1 camera. It does 1200 frames per second, but to make that work, the image size is only 336 by 96 pixels. That also means it needs lots of light to do that. The faster the frames per second, the faster the shutter has to be, so we need some extra light. This first shot here shows how dark it looks with just the existing lighting in my shop. I added two 30-watt LED panels meant for a studio to light up the can even brighter, and this is what that results in, looking a lot better. Here's what those lights look like. As you can tell, 30 watts of LEDs are very bright and helped a lot. Now, assuming we can see the ball in these frames, which is going to be a big smear, I needed a background with lines on it. And what you see here is a piece of corrugated plastic in which I drew lines on it, vertical lines 1 inch apart. Now what you see here is the second version. The first version didn't have the black border along the bottom. So for the first attempt, I thought a white background with a black ball would be the best contrast. So the video you're going to see in a little bit doesn't have that black background, and I had colored the ping pong ball black with a big Sharpie, and let's take a look at how that looked. And boom, did you see that? Let it play a couple of times through so you can see it going by. This is at 1200 frames per second recorded, played back at 30 frames per second, which means it's showing it to you at 40 times actual speed. Now let me drop it down to 1/5 of that, so what would that be? 200 times slower than actual speed, and let you see that. You can see the black smudge moving across your screen. Okay, so here we get to do some math. Make it real science, so you got math and observations. What I did is took the best 2 frames I could find in that video that were back to back, and measure how much the ball moved from one frame to the next. What you see here are those 2 frames, one right above the other, frame 1 and frame 2. Then I drew vertical lines to estimate where the trailing edge of that smudge is, that smudge being the ball going by. And in the top frame, it's further to the right than it is in the bottom frame. And those vertical lines in the background, those are 1 inch apart, and there's a scale down there as well. But that shows that it looks like it moved about 9 inches in one frame. Now at 1200 frames per second, that means it was moving 10,800 inches per second, which comes out to 614 miles an hour. Pretty impressive. That's a rough estimate because that smudge is kind of hard to see, but it's certainly better than nothing. Okay, this is where I switched over to a black background and a white ball because the contrast was pretty low with the first measurement we did. So here you see I've added the black border on the bottom of the scale, and I removed the ruler, the yardstick or whatever, because you couldn't really read the numbers anyway. Now what I'll do is I'll take and find 2 good frames on this and put them back to back like we did the other one. So here we are, and as you can see, the white smudge is a little bit easier to see, at least it is for me. And frame 1 versus frame 2, this time I put the lines measuring the front edge of the smudge, the ball, because there was glare causing it hard to read the back edge. This one looks like it came out to be 9.5 inches thereabouts, so a little faster. That comes out to 11,400 inches per second, which is 648 miles an hour. A couple of interesting things to point out while we're here is the amount of vacuum I was pulling on these shots has been 14.21 psi, pounds per square inch. A perfect vacuum would be 14.7 or thereabouts. That's atmospheric pressure, depending on the weather. And so 14.21 is a pretty strong vacuum for just the little vacuum pump I'm using. Another thing is, notice that the ball that's smeared out is about as long as the distance between frames. That means that the shutter is staying open basically the entire time, the entire frame, the shutter staying open. It could be that's just the way the camera works and manages to get these fast pictures, or it could be that we could still use more light. So later we'll move this outside in some sunlight and see if that gets any better. Okay, now this is a fun little shot. I am going to see if I can measure how fast the ball is going after it goes through a pop can and how fast that pop can is traveling. Then we'll do a little bit of science, math, or whatever on conservation of momentum. Here's the measurement for the ball after it goes through the can. As expected, it has slowed down. On these lines, I drew them on the trailing edge of the smudge, and the smudge is shorter, and it seems to me that it's moved 7 inches in a frame, which comes to 8,400 feet per second, which is 477 miles an hour. Now this is the same shot, but we're measuring the can, and in this case I used 20 frames instead of 1 because it's traveling so much slower. In 20 frames it moved 9 inches. That's 540 inches per second, which is only 31 miles an hour. Okay, now for some fun physics calculations. I talked about conservation of momentum. Well, momentum is equal to mass times velocity, and you can see it hidden down here. Momentum, the big M, is velocity times the mass. Now, in the first case we did, we're taking some rough estimates, so to make math a little easier, let's just say that the ball had the initial muzzle velocity of 600 miles an hour. So the momentum would be 600 times its mass, which right now we don't know what its mass is. Okay. Now after piercing the can, it had dropped to 450 miles an hour. So the velocity went down. That means its total momentum went down too. So if the initial momentum was 600 miles an hour times the mass, it is now 3/4 of that, because 450 miles an hour is 3/4 of 600. Again, this is just rough numbers compared to what we did. So that means 1/4 of that initial momentum was transferred to the can. Now, to be clear, we're not talking about kinetic energy, because kinetic energy isn't conserved in the same way. A lot of the energy goes into tearing and bending the can and heat and all that stuff. But momentum is always conserved. So 1/4 of that momentum went to the can. So based on that, we can estimate what the mass of the can is. So if 1/4 of the momentum of the ball went to the can, well, that 1/4 would be the same as 150 times the mass of the ball, and we measured the speed of the can is 30, so its momentum is 30 times the mass of the can. So if we do the algebra and switch it around, we can find out that the mass of the ball divided by the mass, the mass of the can divided by the mass of the ball is equal to 150 over 30 is equal to 5. So the can weighs 5 times as much as the ball does, according to our formula. So let's check that out. Well, the internet says that a ping pong ball weighs 2.7 grams. Based on that and our calculations here, our can should weigh 13.5 grams. So I ran downstairs and I weighed that can. That can came out to 13.3 grams. Really close to the estimate. And that just tickles me when the math works out. Okay, on these next two shots, I moved the setup outside so that I could get some sun. Unfortunately, this day wasn't clear blue skies. It was overcast, but still bright enough. It was far brighter than inside. So we'll show you how that improved our contrast and made for a better video. Also, the black strip along the bottom, it was just colored in with a fat Sharpie, but this time I painted it with flat black paint, which makes it better as well. So let's take a look at that and see what we can do. Oh, I forgot to mention on these next few shots, well, the earlier shots I was getting 14.21 psi of vacuum for all the shots. For some reason, on these next few shots, I was only able to get 13.96 psi. So I was expecting a little bit slower velocities. So let's see how that goes. Here are the two frames I picked for this one. A couple of things to notice here is, one, the smudge from the ball going by is a lot shorter. It's like half as long as what it was for the other pictures, and that shows that the shutter speed outside is much faster than it was inside, like twice as fast. That also increases the contrast, so it's easier to see the ball, the smudge from the ball, and so we captured both of those things. So the brighter light does increase the shutter speed, which tells me that the camera doesn't always just keep the shutter open in this high speed mode. Now the markings you see here shows that it's roughly 8.75 inches from frame to frame, and maybe a little bit, yeah, that's probably about right. It's 8.75 inches from what it shows there. That comes out to 10,500 inches per second and 597 miles an hour. Now, I predicted that this would be just a little bit slower than the previous ones because the pressure was a little bit less, and it kind of indicates that, although it's almost in the noise. And here's the next outdoor shot, kind of more the same, so let's get into the analysis of that. And here are the results, very similar to the last one. So it comes out to 8.75 inches per frame. 10,500 feet per second is 597 miles an hour. Okay, this next shot is also outside and 13.96 psi, but we're adding an interesting twist. In the previous calculations we did, the ball and the can after impact were going different speeds, so they shared momentum in that way. Now, this time I'm going to fire the ball at the bottom of the can, which is much tougher. I do not expect it to pierce the can, so I'm hoping the two will stick together as they exit the screen so that we can measure the velocity of the two and calculate what that velocity is based on all the masses traveling at the same speed. So let's get into that and see what it looks like. From those videos you just saw while I was talking, it looked like the ball and the can were not stuck together, but they were exiting the screen at pretty close to the same speed, so we can do the math on that. So let's estimate what that velocity is. So the total momentum that we had before was 600 miles an hour times the mass of the ball. Now, since the can and the ball are traveling at the same speed, remember the can was 5 times the mass of the ball. So the total mass traveling as it exits the screen is the mass of the ball times 6. So that's what we have here. So the initial velocity was 600 miles per hour. The initial mass was the mass of the ball. Now we have 6 times the mass, and we want to know the velocity. So if we do the algebra, velocity equals 600 times the mass of the ball divided by 6 times the mass of the ball. That comes out to an estimate of 100 miles an hour. So now let's go measure it and see what it comes out to be. Since this is traveling slower, I decided to go with 4 frames instead of 1, so we get more resolution that way. The starting frame is 1, the ending frame is frame 5. And as you can see there, it traveled a distance of 6 inches in 4 frames, which is 1.5 inches per frame. That comes out to 1,800 inches per second, and that is 102 miles an hour. Now remember, we estimated 100 miles an hour, and that is really, really close. So it's, again, I am really pleased when the physics works. Oh, I forgot to include a picture of the can after impact. It kind of turned the bottom third inside out, and the ball's kind of mangled. So there you go. Okay, a little change of pace here. I promised you a second method for measuring the velocity. I showed you the video method, high-speed video, and now we're going to use aluminum foil strips and an oscilloscope. I built this thing here. The 2x6s along the bottom are to keep everything aligned. These spacers here are 1/2 the thickness of the PVC pipe, and these will hold this will hold the aluminum foil strips. Here is the pipe in place with the cutouts for the end fitting. Here's aluminum foil strips. These are about 1/4 inch wide, heavy duty aluminum foil. I scotch taped them on there just to hold them in place. There's all 3 of them. There's a foot distance between each one of these strips, 1 foot. I then went to overkill. I made these wood blocks to help hold the foil. Later we will learn that that's not really necessary. That's overkill. There's all 3 of them tacked down. Another view of all 3 showing the tube, and a pop can to help absorb the blast if I choose to use it. Here's a fun picture. I decided to look down the length of the tube to see how well lined up this fixture was, and I took this with zoom on my cell phone, and all 3 strips are lined up just about halfway up the tube, and you can see the pop can behind it. Been going through a lot of ping pong balls, so I had to order some more off Amazon. Switching over to PowerPoint here, this is the circuit I came up with to capture the timing using an oscilloscope, and it's attached to this here and to ground. This is a 9-volt battery hooked up to 3 resistors, all of them 10K. And the idea is when the ball breaks these foil strips, you'll get different effects. When you start off with, since this foil strip is grounding where the oscilloscope is, the oscilloscope's going to see 0 volts. Once that strip breaks, Then you have a voltage divider across these two, and the oscilloscope is going to see 4.5 volts. And you need to set your oscilloscope so it triggers off that change from 0 to 4.5. So that's where it triggers the oscilloscope. When foil strip 2 breaks, the oscilloscope's going to go up to 6 volts. And when the third strip breaks, it's going to go to 9 volts. Okay, here we have the actual circuit set up. You can see the ground wire coming around here. 9-volt battery, the oscilloscope, all this fun stuff. Alligator clips in a lot of places, and a little bit of Scotch tape. And there we go. Now, here's where we ran into some problems. When I fired this, I got a good trigger off the first one, and the second one, there was a lot of noise on the scope, but the ball completely missed the third one. And that really surprised me, and I finally deduced that what was happening is the ball flying along here this close to the 2x6, it's catching a lot of air underneath that ball, and it's lifting the ball up so it missed the third strip. So I thought, well, let's try it again. I tried it again a second time, and it went ahead and broke all 3 of them, but the third one was pretty late, so I think it broke as the ball was already past it and just awake from it all. So I decided, well, this isn't going to work. We're going to have to do something different. So, oh, by the way, that's what it looks like when I don't have a pop can there to absorb the impact. This is my garage door on my shop and how far the ball went into it. I checked on the outside, and the steel on the outside was not dented, but it really drove that ping pong ball into the styrofoam. Okay, so what I thought I'd do is I'd lay a piece of wood on top so that it would have the same air forces on top and on bottom of the ball. And it would also help keep the ball going straight. Well, that did the job of keeping the ball going straight, but it captured so much air down that pathway, down the tube down through there, that the ball had slowed down considerably. So this was not apples to apples to what we were doing before. There's just too much drag and stuff going on. So I had to rethink, what am I going to do? Well, I decided to get rid of as much of that wood out there as possible. So I get rid of the 2x6s down below and above, and I trimmed these back where they're a long ways apart and hopefully not interfere with that ball, with the idea that it would let the air get out of the way from in front of the ball as much as possible. And it turned out this one worked. This setup is a good one, and this is the one that I finally got some decent measurements on. And here's what the oscilloscope plot looks like. I should zoom this up. There we go. Zoom it up. Okay, as we talked about, here's 0 volts down here. And we fired the thing, and it breaks the first aluminum foil strip, and it jumps up here to 4.5 volts. Breaks the second strip, goes to 6 volts. Breaks the third strip, and goes to 9 volts, just like we planned. Now, as you notice here, to catch this, I had it set for 500 microseconds per division. And using these cursor controls, that came out to 1170 milliseconds between that first foot. Okay. Let me move to the next one. And the next one is a little slower. From here to here, the second foot was 1240 milliseconds. So that's slower, and we'll talk about that in just a little bit with some calculations. For some fun numbers, that first foot was 1170 microseconds, or 1.170 milliseconds. That's 582 miles an hour average for the foot. The second foot was 1.240 milliseconds. That's averaging 549 miles per hour. That's a loss of 33 miles an hour over a foot. That comes out to about 1,200 Gs, 1,200 times the acceleration due to gravity. Now, based on that acceleration, that means the start of the first foot, again, the average was 582. The start of the first foot, it was doing 597. And at the end of the first foot, it was 567 miles per hour. Now let's do some sanity checks. I checked with ChatGPT and asked it to estimate the drag on that ping pong ball at 600 miles an hour. And assuming a smooth surface and no mock effects, the answer came out to be about 1,000 Gs. We were seeing 1,200. However, that's assuming smooth and no mock effects. The ping pong ball is actually matte, not perfectly smooth. And also, at this speed, we very well could be seeing some mock effects around the ball. What causes that is the speed of air. Even though the ball is traveling less than the speed of sound, we're doing about 0.8 Mach. The air will speed up as it goes around the ball, trying to get out of the way. So we may be seeing some Mach effects. So that would increase the drag considerably. So 1,200 Gs is very reasonable. That 1,200 Gs means that the 2.7 gram ball is feeling 1,200 times its weight. And if you want to do that in kilograms, that's 3.2 kilograms, or in newtons, 31.77 newtons of force trying to slow it down. That's really slowing it down a lot. Likewise, the acceleration in the PVC tube when we're speeding this thing up, reaching 600 miles an hour over 10 feet, the ball is also feeling an average of 1,200 Gs acceleration over that distance. So this ball's not going to go very far. As we mentioned earlier, when I shoot it out into the yard, it only goes out maybe 100 feet out there before it stops. So even though it's traveling somewhere around 600 miles an hour, when it comes out of the cannon, it doesn't go very far out there. Well, that's about all I have to show you. It's been a lot of fun making this video. When you're my age, it's always fun to find a good reason to get out the toys. Be a kid again. I have a philosophy: it's never too late to have a happy childhood. So there. Anyway, I hope you enjoyed it as well. Be sure to hit like and subscribe. Also, I am thinking about maybe doing trying to launch, instead of launching a ping pong ball, what it would take to launch a pop can instead. If you'd like to see that, make sure you ask for that in the comments, and we'll see you around. Thanks.